All right, welcome back to another lecture. In this one, we're going to cover section 3.6, and the topic of discussion is L'Hopital's rule. In the previous two sections, 3.4 and 3.5, we saw some applications of derivatives, doing things like related rates and local linear approximations, right? This section, we're going to talk about limits and how derivatives, being able to take derivatives helps us to compute limits, right? By introducing this rule called L'Hopital's rule. So just as kind of to get the conversation started, let's consider a function like, or let's consider a limit like limit as x approaches infinity of 1 over x squared. Okay, something like this would not be indeterminate, right? This is not indeterminate. We know that as x gets large, x squared is going to get large. Meanwhile, the numerator 1 just remains fixed. And so you have something like 1 over a really huge number, and 1 over a really huge number is a really small number. So over time, as x tends towards infinity, 1 over x squared is going to tend towards 0. So there's nothing indeterminate about that, okay? But imagine instead that you had a situation like you're trying to take the limit as x goes to infinity of something like x squared over e to the x, okay? Now this time it's a little bit more difficult to see what's going on because as x gets really large, x squared is going to get really large and e to the x is also going to get really large. So this kind of goes off towards an infinity over infinity type of situation. And so the question is, well, what happens? Does this go to 1? Does it go to 0? Does it go to infinity? And we're not sure. Right? The answer is we're not really sure in the format that it's in right now. Okay, we would need to do a little bit more work to figure out actually where this limit goes off to, and so we call it an indeterminate. Right? So something of the form infinity over infinity is going to be indeterminate. In a similar way, something like 0 over 0 is indeterminate. Something like 0 times infinity is indeterminate. Basically, anytime you have two pieces of the limit that are exerting conflicting influences on the limit, you're going to end up with something that's indeterminate. Something like 1 to the infinity is indeterminate. That might seem strange at first because you might think, well, 1 to any power is just 1, right? But the important thing to consider is that 1, it's not that the function is just 1 itself. It's that the function is tending towards 1. And so how quickly it does that compared to how quickly the numerator or the exponent goes off to infinity, means that something of the form 1 to the infinity, almost anything could happen. So anyway, that would also be an indeterminate. Something like infinity minus infinity would be indeterminate. Infinity plus infinity is not indeterminate, right? But infinity minus infinity is. Infinity plus infinity would just be infinity. Okay, for example, limit as x approaches 0 from the right of x times ln of x is an indeterminate of the form 0 times infinity. Okay, because as x approaches 0, right, this piece is going to obviously go to 0. And as x goes to 0 from the right, this piece is going to go to negative infinity. Right? This is what natural log of x looks like. So as we approach 0 from the right, we're going down to negative infinity. So it's an indeterminate of the form 0 times infinity, broadly speaking, right? We don't really care if it's negative infinity or positive infinity. We would still say that it's an indeterminate of the form 0 times infinity. On the other hand, something like this second example is not indeterminate at all. Okay, limit as x goes to positive infinity of square root of x times 1 minus x squared. Let's see what this is. This piece is going to go to positive infinity. This piece is going to go to negative infinity, right? 1 minus a really big number is going to be a really big negative number. So this would just be positive infinity times negative infinity, which is just negative infinity, right? That's not indeterminate. It's just negative infinity. Okay, what we would like to do first is we're going to look at indeterminates of the form 0 over 0 and infinity over infinity. Okay, and then once we have a handle on those, we can talk about what to do with these other kinds of indeterminates. Okay, so what we've done in the past, whenever we encountered an indeterminate of the form 0 over 0, is we would just try to do some kind of algebraic trick or maybe some kind of trig to eliminate the 0 in the denominator. We spent a lot of time in chapter 1 learning how to do that sort of thing. But here's a new tool that helps us with those kinds of limits, okay? And it's called L'Hopital's rule, okay? So L'Hopital's rule says that if f and g are both differentiable on an open interval containing a, okay, and if the limit as x approaches a of f of x over g of x is indeterminate of the form 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. In other words, and this is kind of crazy because there's really no reason to think that this might be true until, of course, you've seen a proof. But right off the bat, just kind of a priori, it doesn't seem like this should be the case, and yet it is the case, right? You can just take the you can just take the derivative of the numerator, and you can take the derivative of the denominator independently of one another, and the resulting limit is the same as what you started with, right? It's kind of interesting. Couple things to point out is that this rule only applies to indeterminates of this form, right? They don't apply, you can't do this to other kinds of limits. They only apply to indeterminates of the form 0 over 0 or infinity over infinity. So don't get into the bad habit of just using L'Hopital for everything, okay? Because it doesn't apply to everything. The other thing to keep in mind is that what we're doing here is we're not taking the derivative of the entire function. We're taking the derivative of the numerator and denominator independently. In other words, if we can, let's call this function h, right? Let's call it h of x. Okay, it is not the case that limit as x approaches a of h of x is equal to limit as x approaches a of h prime of x, right? This is not true. Notice that if h of x is f of x over g of x, then h prime of x would have to be h prime of x would have to be f prime g minus f g prime over g squared, right? We would have to use the quotient rule to do that calculation, and that's not what we're doing here, right? We're not using the quotient rule. We're taking the derivative of the numerator and denominator independently. So anyway, with all of those caveats in mind, let's practice using L'Hopital's rule. When I use L'Hopital's rule, I'll usually write an LH above the equal sign on the step where I'm applying L'Hopital's rule. You don't have to do that necessarily, but I think it's helpful. So let's calculate a bunch of these things. So we're supposed to find the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, don't get carried away. As we've said, don't get into the bad habit of just applying L'Hopital right off the bat every time you encounter a limit, okay? Sometimes it applies and sometimes it doesn't. So in the case of part A, if we plug in 2, we're going to get 4 minus 4 over 2 minus 2. 4 minus 4 is 0, 2 minus 2 is 0, so we get a 0 over 0, right, in part A. So L'Hopital's rule does apply here, right? We can apply L'Hopital to this. This would be equivalent to the limit as x approaches 2 of the derivative of the numerator divided by the derivative of the denominator. The derivative of the numerator is just 2x, and the derivative of the denominator is just 1. So in other words, this is the limit as x approaches 2 of 2x, which is just 4. Now in the past, what we would do is we would try to factor this and cancel off a common factor, right? So we would have said, well, this is limit as x approaches 2 of x plus 2 times x minus 2, right? Just factoring out the numerator. And then we would have canceled off the x minus 2's. And we would have been left with limit as x approaches 2 of x plus 2. And sure enough, when you plug in 2, you get 4. Just like we got when we applied L'Hopital's rule. So L'Hopital's rule makes this a little bit easier, you know. Looking at part B, we want to take the limit as x approaches 0 of x squared minus 4 over x minus 2. If we go ahead and substitute 0, we get a negative 4 up here and a negative 2 down there. That's not a 0 over 0. You should not apply L'Hopital's rule here because it's not in the correct form. In fact, this is not even indeterminate. This is just negative 4 over negative 2, which is 2. That's all there is to part B. So again, don't get into the bad habit of just automatically applying L'Hopital every time you encounter a limit. Let's look at part C. We have limit as x approaches 0 from the right of the natural log of x over cosecant x. So in order for us to get a handle on this and determine if we should even be using L'Hopital at all, I think it would be good to maybe write out what the graphs of these things look like. So find some blank space on your notes, and let's remind ourselves that this is what ln of x looks like. And cosecant x. Cosecant has it has asymptotes at 0, and it has asymptotes at the integer multiples of pi, right? So like negative pi and pi, it's going to have asymptotes in those locations as well as at 0. And then cosecant is just it looks like parabolas, right? So it goes like this and like this and so forth, right? It repeats on and on and on forever. So this is y equals cosecant x. Anyway, we're interested in what's happening as x approaches 0 from the right. So let's see. For ln of x, as x approaches 0 from the right, we're going to negative infinity. And for cosecant x, as x approaches 0 from the right, we're going to positive infinity. Okay, so even though we're going to negative infinity in the numerator and positive infinity in the denominator, we would still say that this is an indeterminate of the form infinity over infinity. Okay, we don't care about the signs when we're trying to determine if we've got an indeterminate, right? And in this case, yeah, it would be because it's of the form infinity over infinity. Very well. Okay, so that means that L'Hopital's rule applies. And for L'Hopital's rule, what we do is we just take the derivative of the numerator and the denominator independently. So derivative of ln x is 1 over x. Derivative of cosecant x is negative cosecant cotangent. Okay, now does that help us? Right? Sometimes L'Hopital's rule applies and it's not helpful. In this case, if we go ahead and plug in 0 now, we're still going to get infinity in the numerator. And in the denominator, oh man, cosecant from the right, I think we have some kind of weird infinity thing going on. We can clean this up a little bit, right? We can call this limit as x approaches 0 from the right of negative 1 over x times cosecant x times cotangent x. Okay, so as x approaches 0 from the right, here this part's going to go to 0, but this part's going to go to infinity, so that's an indeterminate. It's not an indeterminate of the form that we can apply L'Hopital to, but it is indeterminate. So this is kind of messy. I'm going to rewrite this, though. I'm more comfortable with secant and tangent than I am with cosecant, or I'm sorry, 1 over cosecant is sine, right? And I'm more comfortable with sine and tangent than I am with cosecant and cotangent. So I'm just going to rewrite this. I'm going to rewrite this as limit as x goes to 0 from the right of sine x tangent x over x. Okay. Well, now this looks familiar. This looks like something that is it's a limit that we already know, right? We know that limit as x approaches 0 of sine x over x is 1, right? So I can take care of that piece of the puzzle pretty easily. This is just limit as x approaches 0 from the right of sine x over x times limit as x approaches 0 from the right of, we'll just call it negative tangent x. And I'll absorb the negative sign into that piece of the puzzle. Because limit as x approaches 0 of sine x over x is just 1. And limit as x approaches 0 of tangent x, that would just be tangent of 0, which is just 0, right? So this is just 1 times 0, which is 0. Anyway, the moral of the story is we only applied L'Hopital to this first step, right? We didn't apply L'Hopital from that point onward. And that just goes to show you that you can't necessarily throw out all of the stuff about limits that you learned about in chapter 1, right? Those techniques are still useful. They might still come in handy, even though we've got a new tool that we also have to work with. Okay, looking at part D. This is another one, I mean, given what we just saw with the sine x over x, right? Limit as x approaches 0 of sine x over x is just 1. So this is something that we could fix up and make it into that format so that we can just use stuff that we already know. But let's see if we can do it using L'Hopital's rule. If we plug in 0, 2 times 0 is 0, and sine of 0 is 0. So we would just have 0 in the numerator, and then, of course, 0 in the denominator. So that means we can apply L'Hopital to this. So let's do that, right? So derivative of sine 2x is going to be cosine 2x times 2, right? Chain rule. So cosine 2x times 2. Derivative of x is just going to be 1. And I think that solves the problem because we don't have a 0 in the denominator anymore. This is just going to be limit as x approaches 0 of 2 cosine of 2x. When we plug in 0, we get 2 times 0 is 0. Cosine of 0 is 1. So this is just 2. Okay. Well, let's look at part E. So we've got limit as x approaches pi over 2 of 1 minus sine x over cosine x. Well, let's see. If we plug in pi over 2, sine of pi over 2 is 1, and 1 minus 1 is 0. So we do indeed get a 0 in the numerator. When we plug in pi over 2 to cosine x, let's see, cosine pi over 2 is also 0. So this is another 0 over 0, which means we can apply L'Hopital to this. So we're going to take the derivative of the numerator, derivative of 1 minus sine x. Well, derivative of 1 is 0. Derivative of negative sine x, I suppose, would be negative cosine x, right? The derivative of cosine x is negative sine x. Okay. Cosine x over sine x is cotangent x, and the negatives will cancel. So we've got limit as x approaches pi over 2 of cotangent x. Okay, so to see what's happening in this situation, it might be helpful to draw a graph. Cotangent has asymptotes in all the same places as the cosecant function that we just looked at a second ago, right? So at 0 and at pi and at negative pi right? It's going to have asymptotes in all of those locations. And then the function itself decreases, right? So it's going to look kind of like this. And it's going to repeat over and over and over again. Okay, so what's happening at pi over 2? Oh, well, nothing, right? At pi over 2, this thing should just be 0. Okay, so cotangent pi over 2 is just 0. So no issue there. I didn't even need to draw the graph. I should have just used a calculator and plugged in pi over 2. I thought we were going to have something interesting going on. Okay, moving on. So this example, part F, is similar to an example that we kind of gave at the beginning. We didn't give the answer, but we just said, what would the limit as x approaches infinity of x over e to the x be? I think we used x squared, though. We said x squared over e to the x, but this is similar, right? If we let x get really large, then the numerator is going to go off to infinity, and the denominator is also going to go off to infinity. And so those things kind of fight against each other. So that makes this an indeterminate. Fortunately for us, it's an indeterminate of the form infinity over infinity, which means we can apply L'Hopital to help us out. All we have to do is take the limit of the numerator, which is 1, and the derivative of the denominator, which is e to the x. Okay. And now we can reevaluate. Okay, if I let x get really large, the numerator is just going to stay 1, but the denominator is going to get really large. It's going to be 1 over a huge number, which is, of course, just 0. In general, an exponential like e to the x is going to dominate a polynomial. So even if you had something like 3x to the 15th power minus 17x to the 14th power plus, x squared, whatever, in the numerator, and you just had a simple e to the x in the denominator, the e to the x is going to win, okay? It's going to dominate and take that thing down to 0. Okay. What about something like tangent x over x squared? I think I've walked you through enough of these examples that you've kind of got the idea now. So what I would do is invite you to go ahead and give the video a pause and see if you can tackle part G on your own. Okay, here's my solution. So as x approaches 0, tangent x is just 0. It's not going to negative infinity or something like that. It's just tangent of 0 is 0. And of course x squared would also be 0. So we have a 0 over 0 type of situation. That's an indeterminate, and so it's going to require L'Hopital. So we'll take the derivative of the numerator and denominator independently. Derivative of tangent x is secant squared x. Derivative of x squared is 2x. Okay. So now let's think about what happens. Secant of 0 is, once again, it's not like infinity or negative infinity or something like that. Secant of 0 is just 1. So secant of 0 squared, right? Secant squared 0 would also just be 1. And meanwhile, the denominator is 0 though, right? So we're going to have to maybe do a little bit of work to see what the limit here is. Let's break this apart. We cannot apply L'Hopital again because it's not 0 over 0, it's 1 over 0, right? So this is limit as x approaches 0 of secant squared x times limit as x approaches 0 of 1 over 2x. It's approaching from the left. Okay, that little detail is important, I think, because 1 over x looks something like this. And so 1 over 2 times x is going to look pretty similar, okay? And so as we're approaching 0 from the left, it looks like this thing is going to go down to negative infinity, okay? This piece goes to 1. This piece goes to negative infinity. So that means this limit is negative infinity. Okay, let's do another one. Limit as x approaches 0 of 1 minus cosine x over x squared. Again, I would invite you to give the video a pause and give this a try on your own. Here's my solution. Okay, we know that the limit as x approaches 0 of 1 minus cosine x over x should just be 0. But let's see what happens when we make it an x squared instead. Okay, so if we plug in 0 as it is now, cosine of 0 is 1, and 1 minus 1 is 0. So we get 0 in the numerator. Of course, we get 0 in the denominator. Well, hey, we can apply L'Hopital. Derivative of 1 minus cosine x. I think that's just going to be a positive sine x, right? Because derivative of 1 is 0. Derivative of cosine x is negative sine x, but we've already got that negative sign, so it'll cancel and make a positive sine x. Derivative of x squared is 2x. Okay, so this is very similar to the previous example, I guess, in some ways. Okay, now limit as x approaches 0, sine x over 2x. Notice that this is another 0 over 0. Okay, if we plug in 0, sine x is 0. If we plug in 0 to 2x, we get 0. So we could actually apply L'Hopital again to see what happens. Okay, you're allowed to apply L'Hopital as many times as you've got a limit of the form 0 over 0 or infinity over infinity. So we'll do it again. Derivative of sine x is cosine x. Derivative of 2x is 2. Okay, limit as x approaches 0 of cosine x. Well, we could just plug in 0 there. Cosine of 0 is 1. So that's just 1/2. And that's it. Okay, isn't that interesting? Maybe we should look at this in Desmos. Okay, so here we are in Desmos, and here's our old familiar 1 minus cosine x over x. You can see that as x approaches 0, 1 minus cosine x over x approaches 0. But what happens when we make it an x squared in the denominator? Oh, okay, something different happens, right? If we zoom in a little bit, yeah, you can see that that is approaching 1/2. Okay, just like we thought. Okay. Part I. Once again, go ahead and give this video a pause and see if you can do part I on your own. Okay, here's my solution. Limit as x approaches infinity of x to the negative 4/3 over sine of 1 over x. Holy schmoly, okay. Well, let's take this a piece at a time. If x gets really large, then x to the negative 4/3, well, x to the negative 4/3 is 1 over x to the positive 4/3, right? 1 over x to the positive 4/3. X to the positive 4/3 is going to go off to infinity as x gets large. So 1 over x to the positive 4/3, that's going to be 1 over a really large number, which is going to be 0, right? So this piece goes to 0. What about sine of 1 over x? Well, as x gets large, 1 over x is going to go to 0, and sine of 0 is going to be 0. So sure enough, we've got a 0 over 0 situation. So that means we can apply L'Hopital to this to see what's going on. The derivative of that numerator is going to be negative 4/3 x to the negative 7/3, right? Negative 4/3 minus 1. Okay, and the derivative of the denominator, let's see, that's going to have to be cosine of 1 over x times the derivative of 1 over x. Well, 1 over x is the same as x to the negative 1, right? And the derivative of x to the negative 1 is going to be negative 1 times x to the negative 2, or in other words, negative 1 over x squared. Okay, so this is times negative 1 over x squared. Okay, let me erase this. Okay. Let's see if we can clean this up a little bit. I'm inclined to want to move this piece by kind of flipping and multiplying. So let's do that, right? This is limit as x approaches positive infinity of negative 4/3 x to the negative 7/3 times negative x squared over cosine of 1 over x. Well, anyway, when you multiply two factors with the same base, you just add their exponents, right? So negative 7/3 plus 2. 2 is 6/3, right? Negative 7/3 plus 6/3, that should just be negative 1/3. The negative signs will also cancel off, so I think this is limit as x approaches infinity of 4/3 x to the negative 1/3 over cosine of 1 over x. Okay, let's see what happens now. As x goes to infinity, x to the negative 1/3 is going to go to 0, because x to the negative 1/3 is 1 over x to the positive 1/3, right? So as x gets large, that's going to get large. In the denominator, we have 1 over a really big number, okay? 1 over a really big number right here, which is going to be 0. But cosine of 0 is not 0. Cosine of 0 is 1. Okay, so the denominator is just going to be 1. The numerator is going to be 0. So this is just going to be 0 over 1, which is 0. Okay, so this is how L'Hopital's rule works. Like with any other limit, this is something that just takes a little bit of practice to get used to. But it is a really nice tool that gets us out of some pickles, okay? One thing that we've already commented on that I think deserves maybe a little bit more formalized statement is this. Limit as x approaches positive infinity of x to the n over e to the x is going to be 0. Right, this is always going to be 0, regardless of how big n is. N could be 1,000,000, but in the long run, e to the x is going to outgrow x to the 1,000,000th power, right? So that means we're going to end up with a limit of 0. And you can see that if you just apply L'Hopital n times. Okay, you'll just end up with 0. For example, limit as x approaches infinity of x to the 4th over e to the x, well, we can apply L'Hopital, right? Because we've got an infinity over infinity type of situation. This is going to be 4x cubed over e to the x, which is infinity over infinity. So again, we can apply L'Hopital's rule. We're going to get 12x squared over e to the x, and you can see where this is going, right? The numerator is changing. The degree in the numerator is decreasing each time. Meanwhile, the denominator remains unchanged. So this is going to be 24x over e to the x. Another application of L'Hopital gets us to 24 over e to the x. Now the numerator is just a constant, and the denominator is getting really large, so clearly this is going to go to 0, okay? Now, if you flip this the other way around and you put e to the x in the numerator and x to the n in the denominator, then by the same line of reasoning, e to the x is going to dominate eventually, and this thing will go to infinity, right? So e to the x over x to the n goes to infinity, x to the n over e to the x goes to 0. Okay, let's talk about other kinds of indeterminates. If you have something like 0 times infinity or infinity minus infinity, then usually the trick on those is to manipulate them algebraically into something that we can use L'Hopital on. We wouldn't be able to use L'Hopital on a limit of this form because in order to use L'Hopital, we have to have 0 over 0 or infinity over infinity. So can't use L'Hopital on these, but we can maybe do some algebra on them to get them into a format where we can use L'Hopital. Okay, and so that's going to be the strategy whenever you encounter 0 times infinity or infinity minus infinity, right? That's the strategy. Get them into a format where we can apply L'Hopital. Let me just show you how that's done, okay? For number 2, part A, we have the limit as x approaches 0 from the right of x times ln x. This piece goes to 0 as x goes to 0. This piece goes to negative infinity. So this is a 0 times negative infinity, or in other words, just a 0 times infinity type of situation that we're in. Okay, so we cannot apply L'Hopital because for L'Hopital we need 0 over 0 or infinity over infinity. But what we can do is we can do a clever little trick. And the trick is this. You can always take one of these products and rewrite it as a quotient. Okay? So in other words, instead of thinking of this as x times ln of x, we could think of this as ln of x divided by 1 over x. Okay? Or we could think of it as x divided by 1 over ln of x. Okay? I'll let you kind of pause the video and think through that for a second. Now, of those two choices, when we apply L'Hopital, we would like to make the derivative as simple as possible. And so I'd rather leave ln of x in the numerator and put 1 over x in the denominator. Again, verifying that this is the same, notice that in order to carry out this big division, what we would do is we would take this and we would flip and multiply. Okay? And we would end up with ln of x times x, which is just exactly what we started with, right? So what we have now is the same as what we started with, even though it looks dramatically different. And here's the beauty of doing that, because now, if we think about what's happening as x approaches 0, ln of x is going to negative infinity. And 1 over x, as we approach 0 from the right, 1 over x is going to positive infinity. So they're going to different infinities, but that doesn't matter because that would just, that doesn't matter. It's still an indeterminate of the form infinity over infinity. We can still apply L'Hopital to this, in other words. So let's do that. Okay, so derivative of ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. We just saw it a second ago, right? Okay. Well, now let's carry out that division. Okay, we can see that this is going to be limit as x approaches 0 from the right of just negative x when all is said and done, which is of course just 0. Okay, so that's the trick on these. You can always do something like this whenever you have something that's of the form 0 times infinity. Let's see another example. For part B, we have limit as x approaches pi over 4 of 1 minus tangent x times secant of 2x. Well, if we plug in pi over 4, tangent of pi over 4 is 1. So 1 minus tangent of pi over 4 is going to be 0. Meanwhile, secant of 2x, well, if we plug in pi over 4, 2 times pi over 4 is pi over 2. Okay. Secant has an asymptote at pi over 2, right? So the limit does not exist there. If we approach from the left, it's going to go to negative infinity. And if we approach pi over 4 from the right, it's going to go off to positive infinity. So the limit doesn't exist. Now, in this case, the limit doesn't exist because it's approaching positive infinity from one direction and negative infinity from the other direction. And so kind of broadly speaking, we could think of this as being infinite, an infinite limit. If you were looking at something that just where the limit truly doesn't exist, right? Where the limit, where x is bouncing back and forth between -1 and +1 or something like that, well, then you wouldn't not be able to apply L'Hopital to that kind of limit. But you can apply L'Hopital to this one, or rather, I'm getting ahead of myself. You can fix this up. You can fix it up algebraically so that it gets into a format where L'Hopital applies, okay? And I think the trick to doing that is, in this case, to notice that secant is just 1 over cosine. So I can rewrite this as 1 minus tangent x over cosine of 2x. Okay, now the numerator is going to be 0. The denominator, if we plug in pi over 4, 2 times pi over 4 is pi over 2. And cosine of pi over 2 is 0. So we have 0 over 0. So we can apply L'Hopital. Derivative of tangent is secant squared. So the derivative of that numerator is just going to be negative secant squared x. In the denominator, derivative of cosine is negative sine. Okay, so this is going to be negative sine 2x. And then we should take the derivative of the inner function, right? Chain rule. So we would multiply by 2. I'm just going to go ahead and pop that 2 in front here. So we've got negative 2 sine 2x. Okay, the negatives cancel, obviously. But what happens when we plug in pi over 4? So secant pi over 4, let's see. Secant pi over 4. Secant is 1 over cosine, and I know that cosine of pi over 4 is root 2 over 2, or in other words, just 1 over root 2. So that means secant of pi over 4 should just be square root of 2. Okay, so this is going to be square root of 2 squared, and it's negative. Okay. In the denominator, if we plug in pi over 4, 2 times pi over 4 is pi over 2, and sine of pi over 2 is 1, and 1 times negative 2 is, well, it's just negative 2 times 1. Okay, so I'm not getting any zeros here. I think that we're safe. This is going to be negative 2 over negative 2, which is positive 1, and that's it. Okay, so that limit is positive 1. Okay, so this is how you handle situations when you've got a 0 times infinity format. What about infinity minus infinity, like in parts C and D? Okay, when we approach 0 from the right, 1 over x is going to go to positive infinity. Okay, and 1 over sine of x is also going to go off to positive infinity. Okay, and so we have an infinity minus infinity situation here. With these types of situations, usually finding a common denominator and then combining those two fractions will do the trick. So let's try that. If that doesn't work, we could maybe try multiplying by a conjugate or something along those lines. But let's try just adding those two fractions, or subtracting them rather. Okay, in order to do that, we need a common denominator, so I need a sine x here, And here I just need an x. And then our denominators will be x sine x, okay? And our numerators will be sine x minus x. Okay, can we apply L'Hopital? Or do we even need to? Okay, what happens when we plug in 0? Well, sine x is 0, and of course x is 0, and 0 minus 0 is 0, so we just get a 0 in the numerator. In the denominator, sine x is 0, or sorry, sine 0 is 0, and of course 0 times 0 would also be 0. So we've got 0 over 0. We can indeed apply L'Hopital, and I think we need to because 0 over 0 is indeterminate. So let's apply L'Hopital to this. Derivative of sine x is cosine x. Derivative of x is 1. In the denominator, we'll need the product rule, right? So it's the derivative of the first times the second plus the first times the derivative of the second. Okay. Okay. What happens when we plug in 0 now? If we plug in 0, sine of 0 is 0, and cosine of 0 is 1, but 1 times 0 would still be 0. We get a 0 plus 0, which is 0 in the denominator. Okay, but we also get a 0 in the numerator, don't we? Because cosine of 0 is 1, and 1 minus 1 is 0. Okay, well, that means that we could apply L'Hopital again. Maybe it's useful, maybe it's not. Let's see. Okay, so derivative of cosine x is negative sine x. Derivative of negative 1 is just 0, so I'll leave that off. Derivative of sine x is cosine x. And the derivative of x cosine x. Okay, we'll need the product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. Okay, let's clean it up. We have negative sine x over 2 cosine x, right? Cosine x plus cosine x, and then minus x sine x. Okay, well now what happens? Now when we plug in 0 in the denominator, cosine of 0 is 1, and 2 times 1 is 2. Sine of 0 is 0, and of course, when we plug in 0 for x, we get 0. So 0 times 0 is 0. This is just 2 minus 0, which is 2. Well, that's not going to be indeterminate, right? Because our denominator isn't 0. In the numerator, we get sine of 0 is 0. So we just get, looks like we just get 0 over 2, which is 0. Okay. So let's look at part D. We have limit as x approaches 0 from the left of 1 over x minus 1 over x squared. Okay, let's take a look at these graphs. Here's 1 over x. And here's 1 over x squared. Roughly, right? So as we approach 0 from the left, 1 over x is going down to negative infinity. As we approach 1 over x squared from the left, we're going to, it looks like we're going to positive infinity. Okay. So we have negative infinity minus infinity. Well, that's not indeterminate at all, right? Infinity minus infinity is indeterminate, but but negative infinity minus infinity, that's just negative infinity, right? That just means you're going down to infinity that much faster. Okay, so that's that. Once again, don't get carried away. Don't get carried away doing all of these crazy techniques if you don't need to, right? If the limit is just a straightforward limit, if it's not indeterminate, then you don't need to do anything crazy. Just plug in the value. Okay, last topic. These are the remaining indeterminates, right? Indeterminates where you have something going on in the exponent, 0 to the 0, or 1 to the infinity, or infinity to the 0, right? These are all indeterminate. For these, we're going to try logarithmic differentiation, okay? For example, in part A, we have limit as x approaches positive infinity of x to the 1 over x. If we let x get really large, then this part's going to get really large, and this part's going to get really small. In other words, we've got an infinity to the 0 type of situation, which is indeterminate, okay? Infinity to the 0. Think about it. The base is getting really large while the exponent is getting really small. So which one wins? Does the exponent win? Does the base win? Well, it probably depends on the expression you're working with. But for sure, this is indeterminate. So we're going to try some logarithmic differentiation here. What we'll do is we'll let y equal this limit. And then we'll take the natural log of both sides. Natural log is continuous, so we can move that inside of the limit. And the nice thing about doing that is that now we can take the exponent down, right? We can use properties of logarithms to take this exponent down in front. So let's do it. Okay, so after using some properties of logarithms and then simplifying a bit, we have limit as x goes to positive infinity of ln x over x. As x gets really large, ln of x gets really large, and of course so does x. So this is now an indeterminate of the form infinity over infinity, and we can use L'Hopital on that. Okay, so let's apply L'Hopital. We'll take the derivative of the top and the derivative of the bottom. Okay, no big deal. Okay, well now what happens? If we let x get really large, 1 over x goes to 0, right? So we have ln of y equals 0. We're not done though, because that's not the limit of that we were originally looking for. That was the limit of the natural log of what we were originally looking for. The limit itself was just y, not ln of y. So we've got to solve for y. And the way that we do that is, well, we just exponentiate. Okay, that'll cancel off those things. So y equals e to the 0. Or in other words, y equals 1. And that's our limit, right? Maybe just to make it come full circle, we can say, well, y was just equal to the limit as x approaches positive infinity of x to the 1 over x. And so we've just proven that that limit is equal to 1. Okay, so that's the trick on these. We do some, we use some logarithms. And you know, I actually kind of misspoke because it's not exactly logarithmic differentiation that we're doing. We're really just taking logarithms. Maybe we try taking ln of both sides. And usually what happens is that you're able to rewrite the thing that you've taken the natural log of in the form, you can rewrite it in the form of 0 over 0 or infinity over infinity. Let's see one other example of this. So for part B, we want the limit as x approaches 0 of 1 plus sine x to the 1 over x. If we go ahead and plug in 0, this is going to be 1, right? Because sine 0 is 0, 1 plus 0 is 1. So we get 1 to the 1 over x, 1 over 0, right? As x gets really close to 0, we're plugging in a very small number here. 1 over a very small number is a very big number. So this would be a big number. So this is an indeterminate of the form 1 to the infinity. We're going to try the same trick that we did before. Okay, we'll set this thing equal to y. And then we'll take the natural log of both sides. All right, after using properties of logarithms to rewrite the expression, we end up with this scenario. ln of 1 plus sine x over x. If we let x go to 0, sine x will go to 0, and 1 plus 0 will be 0, and ln of 1 would be 0. So this entire numerator goes to 0, and of course, so does the denominator. And so we can apply L'Hopital again, right? So let's, or not again, we can apply L'Hopital, right? We haven't applied it yet, but we can go ahead and apply L'Hopital. And okay, let's see, the derivative of the numerator is going to be a little bit nasty. It's going to be 1 over 1 plus sine x times the derivative of 1 plus sine x, which is cosine x. Okay, that wasn't so bad. The derivative of the denominator, x, is just 1. Okay, so ln of y equals limit as x approaches 0 of cosine x over 1 plus sine x. Okay, so now if we let x go to 0, cosine x is just 1. Sine x is 0, but 0 plus 1 is just 1. Oh, so this is just 1, right? ln of y equals 1. So now, when we go to solve for y, we see that y equals e to the first power, which is, of course, just e. So, limit as x approaches 0 of 1 plus sine x to the 1 over x equals e. So there you go, right? That's L'Hopital's rule. That's how it gets us out of a lot of jams, okay? It's a very useful tool. It doesn't always apply. It only applies to indeterminates of the form 0 over 0 or infinity over infinity. But we can often take other kinds of indeterminates like this one, 1 to the infinity, and we can rewrite it in such a way that L'Hopital's rule will apply, and then that'll get us out of some jams. So you'll have a lot of limits. You'll be revisiting limits in the homework for this section, but this time with L'Hopital in hand, hopefully things are a little bit easier. Okay, so that'll do it for this section, and that'll also do it for chapter 3. The next section we'll cover will be 4.1. So we'll be talking about graphing curves and things like that. I really enjoy chapter 4, so it's one of my favorite parts of the course. Anyway, but I also enjoy L'Hopital's rule, of course, don't get me wrong. Thanks for hanging in there, and we'll check in with you in the next lecture.